I'm Nam. Today, I and Jun analyze a pendulum striking a block on a table, a classic impact problem that lets us verify the kinetic friction coefficient without directly measuring impact forces. So first we have a pendulum bob of mass m at the end of a rigid rod of length Lp. It is released from rest and swings down to strike a rectangular block of mass m resting on a table. The impact occurs at a height defined by k times L1y, where k ranges from 0 at the bottom to 1, which means at the top of the object. And after the impact, the block slides along the table with kinetic friction coefficient Vk equals to 0.3. The question is, can we calculate that coefficient from just the block sliding distance and duration plus the pendulum rebounds height? So here is our free body diagram. At the impact instant, the impact force acts rightward on the block. Weight pulls down and the table push up with normal force N, and friction opposes motion. The kinetic diagram shows the mass times acceleration effect at the center of mass in the no tipping regime that tasks 1 through 3. The block is constrained to translation only, so no rotation occurs. Boundary conditions. Here its positive x is rightward, the direction of swing and block motion, and the pendulum angle theta is equals to 0 exactly at impact.
For classical principles, one per phase. Phase A, pendulum swing down, energy conservation gives impact velocity. V subscript P1 equals square root of 2 GHO, where GHO is the bob starting height above impact. Phase B, the collision itself. Impact duration is only about 1 millisecond, so gravity and friction impulses are negligible. Linear momentum of bob plus block is conserved. Phase C, pendulum rebound. After impact, the bob swings to its first stationary point at height h3. Energy conservation gives the rebound speed absolute V subscript P2 equals square root of 2 gh3. The sign tells us if it bounces back. Here it does. Phase D, block sliding. Once moving, kinetic friction alone decelerates the block at A subscript B equal minus mu subscript K multiplied by G. This constant deceleration gives us simple kinetic equations for sliding distance and stopping time. And running the Simulink model with the 4 parameters, m equal 1 kilograms, capital M equals 3 kilograms, give us log positions and velocity data. Dash 3 extract 4 key measurements automatically. First HO from the pendulum initial height, about 0.525 meters, giving V subscript P1 of 3.209 meters per second. Second, H3 from the rebound peak, about 0.022 meters, giving P subscript P2 of negative 0.66 meters per second. Third, the block sliding distance d and duration t dir from the block scope, about 0.28 meters over 0.44 seconds. We invert the sliding equation to solve for mu subscript k, plugging our value in give mu subscript k extract equals 0.304. Compare it to the input value of 0.3, that's only 1.2% difference. This verifies our entire 4-phase analytical chain work end-to-end without ever needing a coefficients of restitution model.
In summary, we have shown that by combining energy conservation, momentum conservation, and Coulomb friction kinematics, we can extract the kinematic friction coefficient to within 1.2% of the true value. The method works because each phase uses directly measurable quantities from the simulation, like H0, H3, D, and T underscore duration, and requires no impact force measurement at all. And thank you for watching.